Imagine this, a man struggling to push his car out of the snow while a happy boy pulls his Christmas sleigh. Who is doing more work? The answer might surprise you, so let's find it out. In physics, work is done when a force is applied on an object and that object moves. Let's take an example to understand this. A man is pushing a car with a force of 500 newtons and the car moves forward by 5 meters. To calculate work, we simply multiply the amount of force by the amount of displacement. In this case, work is 500 newtons multiplied by 5 meters. That gives us a work of 2500 Newton meter. Newton meter is a unit of work. Newton meter is also known as a joule, so we can write the work as 2500 joules. That's great. Let's have a look at another example. In this example, the man is pushing on a car with all his strength, but the car doesn't move because it's broken. In this case, while the man is applying a force of 500 newtons, the displacement is 0 meters because the car doesn't move. Using the same equation for work as force times displacement, we get a value of 500 newtons times 0 meters. That gives us a value of 0 joules. Even though the man appears to be working hard, in the physics sense, no work is being done because there is no displacement. This highlights an important point in physics. No moment means no work. No matter how much effort is applied, if the displacement is 0, the work will always be 0. Work requires both force and displacement. Alright, let's take a look at another interesting example. Here, an apple with a mass of 2 kilograms falls from a tree and drops a distance of 3 meters. We want to calculate the work done by gravity during its fall. The force acting on the apple is the force of gravity, which we can calculate using the formula F equals m times g. This is the same as the weight of the apple. M here stands for the mass of the apple and g is the acceleration due to gravity. That has a constant value of 9.8 meters per second square. Substituting the values, we get F equals 2 kilograms times 9.8 meters per second square, which gives us a value of about 19.6 newtons. Great. Now we have the force, we have the displacement. We can calculate the work done by gravity using the same formula of force times displacement. Substituting the values, we get 19.6 times 3 meters, and the work done by the gravity on the apple is thus 58.8 joules. This means that gravity transfers 58.8 joules of energy to the apple during its fall, which increases its kinetic energy as it moves downwards. Is it possible for force and displacement to be along different directions? What do you think? Let's take an example to understand this. Here's an example. A man is pulling a sled with a rope. The force he applies is along the rope, but the sled moves forward. In this case, the force and displacement are at an angle to each other. When the force and displacement are not in the same direction, we need to modify the equation for work to account for the angle in between. The formula becomes force times displacement times cosine theta. Here cosine theta adjusts for the angle between the force and displacement. Only the component of the force that's in the direction of displacement contributes to the work done. The equation we have is force times displacement times cosine theta then. Let's look at another example in which the force and displacement are at an angle. A boy carrying Christmas presents walks a distance of 50 meters while applying an upward force of 50 newtons to hold the presents. Here's the key question. Is any work being done by the boy on the presents? What do you think? To answer this, we must use the formula for work, which is F times D times cosine theta. In this case, the force applied by the boy is vertical, but the displacement is horizontal, meaning the angle between them is 90 degrees. So we have work equals 20 newtons times 50 meters times cosine 90. And we know that cosine 90 is 0. So the work done by the boy on the presents is 0 joules. This is because the force and displacement are at right angles, and only the component of the force in the direction of displacement contributes to work. Since there is no such component here, the work done is 0. This means that whenever force and displacement are at right angles, the work done is always 0. Now let's look at a ball rolling on a road. The ball moves a distance of 5 meters before coming to rest because of friction. The frictional force acting on the ball is 6 newtons and it opposes the motion of the ball. Let's calculate the work done by friction on the ball. In this case, the force of friction acts in the opposite direction to the displacement. So the angle between them is 180 degrees. We use the equation for work, which is force times displacement times cosine 180 degrees. Since cosine 180 is minus 1, we get work as 6 newtons times 5 meters times minus 1, which can be rewritten as minus 6 newtons times 5 meters. This means that work is simply negative force times displacement. That gives us a value of minus 30 joules. Whenever the force and displacement are anti-parallel, meaning they point in completely opposite directions, work is simply negative force times displacement. Let's take another example in which the angle between force and displacement is less than 90 degrees. Here we have a husky pulling a sleigh by applying a force of 6 newtons. The sleigh moves forward a distance of 4 meters and the rope is at an angle of 30 degrees with the displacement. We want to find the work done by the husky on the sleigh. The work done is given by the same formula. Work equals force times displacement times cosine theta. So we have 6 newtons times 4 meters times cosine 30. That gives us a value of 20.7 joules. This means that whenever the angle is less than 90, meaning it's acute, the work done will be positive. Let's make a recap of what we have done so far. When the force and displacement are in the same direction, the formula for work simplifies to force times displacement. But when the force and displacement are at an angle, we use the general formula, force times displacement times cosine theta. If the angle is 90 degrees, that is the force and displacement are perpendicular to one another, the work done would be 0. If theta is less than 90 degrees, the force has a component in the same direction as the displacement. This results in positive work as cosine theta is positive. Finally, when the angle theta is greater than 90, the force has a component opposite to the displacement. This results in negative work. Now that you have understood how work depends on force and displacement and the angle between them, you're ready to tackle even more challenging problems. Great work! If you enjoyed this video, hit like and subscribe for more physics fun. See you in the next one.